Hi, welcome to the 42nd module for the course, and this is the last module for this week. In this module what we are going to do is we are going to put the whole thing in a test bench and check that the design that we designed earlier is correct or not. So when you design test benches, one of the things that you have to do is come up with what is called a test plan. So remember, we agreed on some kind of a protocol between the machine that we designed and the external world. Unless you do that, we cannot expect the machine that we design to work under all possible conditions. So some of the protocols that we agreed on are that if the state machine is still working, then we are not supposed to give more inputs, right. So this is some protocol that we have to agree on, and because if we do not agree on that, then we can keep giving inputs at any point of time. The other thing that we agreed on is we will give the inputs and then we will turn on the go signal, so that the inputs become stable. We agreed on that. So we will have to come up with a test plan which takes care of all of these things. So what I have done is I have written down a tentative test plan for this for testing this particular design. So the test plan is like this. I will start with resetting the chip. So the first thing that we need to do is reset the chip, because if the chip is not reset, then it is not expected to work anyway. So once we reset the chip, we place the inputs. Once the inputs are placed, we can turn on go, right, which means from the external world point of view, there is the inputs are ready. However, this does not mean that the state machine can start working. So it is possible that we need to wait for the state machine to finish. So we will wait till this done signal becomes 0. For whatever reason, if done is 1, we will have to wait till done equal to 0. At this point we remove go. So once you remove go, the state machine will start running. The state machine it starts working. We will have to wait again till done becomes 1. So that is the 6th point. We will wait till done becomes 1, and once done becomes 1, the output is ready. If the output is ready, we may have to copy it, print it, whatever. In the simulation we will go and print it. If you actually design a chip which needs GCD, it will take the output and maybe copy it locally and whatnot, and then it is ready to go back and place the next set of inputs. So what we are going to do is we are going to follow this protocol. We will reset the chip, place the inputs, turn on the go signal, wait till the done signal becomes 0, because if it is not 0, it means that there is something that is happening in the chip, and once that is over, we then remove go, which means this is a pulse that is given to the state machine. The pulse comes and goes, the state machine will start working, and then we can do the rest of the stuff. So this is what we are going to do in the test bench. So what I have done is I have already written this test bench now. So just the test bench, the test harness is relatively simple to write. I have already written the test bench. So the test bench has clock, reset and go, which are supposed to be given as inputs to the machine that I designed, and it has 2 inputs which are supposed to be locally generated within the test bench. There is an output that is supposed to be coming out, and there is also a done signal that is coming out from the GCD machine itself. So the GCD machine has clock, reset, go, input 1, input 2, which are all going in, output and done which are coming out. And I have written a small always block which simulates the notion of a clock. So all this does is it makes clock equal to 0, wait for 25 units, make clock equal to 1, wait for 25 units, and then repeats this over and over, which means this is a clock of width 50 time units. Then this part of the code takes care of printing waveforms and whatnot. Let us see whether the test plan is correct or not. So we initially make reset equals to 1. So we first go and reset the chip, and we ensure that the go signal is 0. Right? So the go signal is 0, and then we wait for this hash 100 means wait for 100 time units. If you go and look at the clock period, it is 50 time units. So we are having the reset on for 2 clock cycles. Once the reset is gone, we pull down reset. So, the resetting the chip means bring it to 1 and then bring it back to 0, right. So, that will reset the chip. At this point all the registers will have 0, and if you remember the state register also has a reset input, it will go to 0 0 0 and 0 0 0 is for state S0. So, this will take it to state S0. At this point go to is 0, which means it will loop back in state S0 itself. Then we go and place the inputs. So, this is the second part of the test plan. Place the inputs. In this case I am testing the GCD of 10 and 5. So, I am giving 10 and 5 and I am giving 2 cycles as steady value. So, for 2 cycles 10 and 5 will be placed steadily at the input of the data path. Then I make go to equal to 1. So, that is the third step, right, turn on go. The fourth step says wait till done equal to 0. So, wait till done equal to 0 is equivalent to while done equal to 1 wait, right. So, if you have to wait till some condition happens, then it is as good as saying while the negation of the condition is happening wait. So, this is checking while done t equals 1 then wait. It means we are expecting, so if you are in state S0, right, for whatever reason the done signal is not 1, right, then there is some faulty condition. So, at the S0 state I think we initialized done to 1, let me go check. In the S0 state, so it looks like I have not made done equal to 1 in the start state, in the S0 state. So, I will make that 1, save it. So, if I go back to the controller now, if I go back to the controller, so the controller is going to wait when the done signal is 1, which means for whatever reason the state S0, if you are not there it will wait till S0 is till you are in S0 state, and then when we remove the go to signal, so if we remove the go to signal, go to was 1, at this point when go to equal to 0 the state machine starts working, right. So, at this point the state machine starts working and the state machine is supposed to change a lot of things and then finally bring it to the done state. At the when it goes to the final thing again done becomes 1. So, we will have to keep waiting in the test bench till the done becomes 1. So, while done t is not equal to 1, at this point we are saying that if it is not equal to 1 then the state machine is still working. So, I will have to wait, and when we exit this while loop we are ready to print out the output. So, when we exit the while loop we know that done is actually equal to 1, at this point the output is correct. So, this is the basic test bench plan. So, again let us go and look at the review the plan. Reset the chip, place the inputs, turn on go, wait till done becomes 0, because if done is not equal to 0 there is something wrong, right. Wait till done becomes 0, once done becomes 0 you remove the go signal, FSM will actually start working, and then we wait till done equal to 1, because at this point the state machine is working. Now we have to wait for done becoming 1, and when you come out of that output is ready and we can print it or view it or whatever. And what that enables us to do is another interesting thing. Once output is ready we can actually go back and place the next set of inputs. So, let me first try this, I will run this and try. So, it is opening a waveform, let me get the appropriate signals. In the GCD machine I need clock, reset, the 2 inputs, go, done and the output. So, these are all the things that my GCD machine has. So, I select all of them and let us look at it. So, clock seems to be something that is periodic, and let me rearrange the signal so that it will make some logical sense. So, I am going to bring the reset to the very top and done should go to somewhere on the bottom, the 2 inputs, okay. So, this is logically sequenced now. So, according to the test plan I will initially reset the chip, which means I reset the chip and I put it at 1 and I bring it down to 0. So, the reset part of the test plan is correct. once the reset is done, I am going to place the inputs. So, in this case I am placing the input A and 5. So, A is for 10 and B is for 5. So, I can convert the radix. So, okay, it seems to be only in hex and binary. So, let us leave it at hex itself. So, this is 10 and this is 5. So, we have 10 and 5. Once these are ready, I am making go equal to 1. So, go becomes 1, and when go becomes 1, it is checking what the done signal is. The done signal happens to go to 0. So, go also becomes 0. So, go becomes 0. At this point the state machine is beginning to work. The state machine is doing its work for whatever number of cycles, and it is ready to give the output. At that point done becomes 1, and when done becomes 1, you can see that the output that you are supposed to get is 5. So, done becomes 1 and this output becomes 5. So, it looks like it is okay so far. So, I am going to try another set of inputs. So, I can actually go and place another set of inputs now, right. So, what I will do is I will copy from here with a new set of inputs. So, and let us say I am going to put let me put this. So, 243 minus 144. So, I am going to put some other numbers 243 and 144. So, in this case I think it's they both are divisible by 3. So, let us see what the GCD is supposed to be. Then again I save it, run. So, the waveform is opening up. Let us get the signals once more. So, again all these signals are of interest to me except the output enable signal. So, let us see what has happened. So, again I am going to reorder all of these. So, reset goes to the very top, go goes next, done goes to the bottom, and the inputs also climb up. So, go can go down. Yeah, okay. So, let us look at this now. So, we have the clock, the reset went to 0, then we place the two inputs A and 5, we give a go, the done signal becomes 0 because it is not done. At some point it becomes 1, which means at that point I can go and read the output is 5. Once that becomes 1, my test bench is giving the new inputs. So, these are my new inputs, this is 243 and this is 90, 90 is 144. So, 90 in hexadecimal is 144, F3 is 243. So, I have given 243 and 90 or 144 as inputs, then I again give a go. When I give a go, then the done signal again is pulled down to 0 by the state machine. It is now taking more time. So, GCD of 10,5 can actually be resolved with only one subtraction, whereas GCD of 243 and 144 cannot be resolved with one subtraction. So, 243 and 144, it takes a bunch of cycles and then finally the done becomes 1. At this point the output is 9. So, in fact, if you want to go and see the state transition itself, you can go and look at the state registers inside the controller. So, the controller has two state registers. We can look at just the C state, which is the current state. Let me append that. If you look at C state and if you expand it, you will notice that they are having some nice transitions that are displayed. So, let us go and look at this. So, initially we are in, let me move it to the left. So, I move it all the way to the left. So, it looks like initially the state machine is in S0. When go goes high, it goes to S1. which is what we expected from the state diagram. Then it goes to S2, it goes to S3. So, we gave 10 and 5 as inputs. From S3 it goes to S4 because 10 is greater than 5, then it goes to S6. So, at this point we have done 10 equals 10 minus 5. It again you come and check, at this point 10 is equal 10 minus 5 is 5 and you are comparing, you are getting GCD of 5 and 5. So, it goes to S7 and S7 is the final state, and from there we go to S0. So, this seems to be the case for 10 and 5. So, at this point we are giving 243 and 144 as inputs. So, 243 is greater than 144. So, 243 minus 144, that is done here, right. So, 243 minus 144 is 99. So, so it goes to state 4 and state 6. Then we have 99 and 144. So, if you look at 99 and 144, then again 99 is greater than 144. So, sorry, 99 is lesser than 144. So, if 99 is lesser than 144, from this state 3 it goes to 5 because 99 is less than 144. So, 144 minus 99 is 45. So, it goes to state 6. Then you are comparing 99 with 45. So, from there on it continues, 99 and 45 you compare, then you will compare 45 and so on. So, this goes on forever till the final result comes through. So, at the very end if you notice, the final result is 9. So, 99 minus 45 is 54, sorry, not 44, and if you keep repeating that, eventually you will end up with 9. So, you can see the state transitions in C state if you want to. So, what we have done is, in this week we have done something very different from the rest of the weeks. First of all, there were no PowerPoint slides. So, you have to see the video to do these things, right. The other thing is I am going to supply the Verilog files to you. So, if you want to go back and change things and manipulate and so on, you are ready to do it. In fact, I designed a what is called a Mealy machine. You can go and see if it can be converted to a Moore machine easily. So, my suspicion is it is actually easily convertible to a Moore machine. I would suggest that you go and try it, take the Verilog files and play with it. But what we have done is, from a design problem that is specified as an algorithm, I converted that to a state diagram, to the appropriate data path, connected all of them together, wrote the Verilog code for all of that and took it to a stage where it can be simulated and where the results can be seen. So, this is quite a leap from the previous set of classes, but this is interesting and important because this is what designers in the real world do. They design state machines, sometimes not just one state machine, they design multiple interacting state machines which all take care of moving data from one place to the other at the right points of time to get some computation done. So, what we will see in the next class is a minor variation of the state machine, and then we will go on to an interesting topic, namely pipelining and parallelism. So, this will be the contents for week 8. We will see what it means to pipeline a circuit, what it means to parallelize a circuit, and what are the design choices in doing that. But this week is supposed to give you material on state machines, and you have seen that in elaborate detail. I suggest that you take a problem on your own and try and do something like this. So, maybe I will post something on the forum later which suggests a problem on which you can work on a state machine. Of course, you will also have homework problems which are all on state machines for the week 7. So, thank you very much, and I will see you in the next week. Bye bye.